These are the hands of gifted craftsmen, scientists, creative engineers, test pilots, secretaries, doctors, accountants, artists. These are the hands of men and women welded into a team of extraordinary competence, working in the fascinating fields of aeronautics, astronautics, automation, and electronics. These are the men and women of McDonnell Aircraft of St. Louis, Missouri, aged 25, a free enterprise dedicated to the service of the community, the nation, and the free world. The story of this company has few parallels in the annals of industrial history. It is the story of a small two-story office building expanded to a vast plant of 5 million gross square feet of floor area, of a team of 2 grown to a team of 34,000, of 0 sales in the first year to cumulative sales of more than $4.5 billion only 25 years later. But mostly, it is the story of creative achievement in research, design, development, manufacture, and testing, and of a team working together on missions vital to the nation's defense and status in space exploration. In the sprawling plant that adjoins St. Louis Lambert Municipal Airport, the McDonnell Aircraft team is involved in some of man's greatest adventures, aircraft that fly at 2.5 times the speed of sound, that reach altitudes in excess of 100,000 feet, manned spacecraft designed to rendezvous with other vehicles in orbit and remain in orbit up to 2 weeks, hypersonic glide re-entry vehicles, which determine the effects of re-entry into the atmosphere on winged space vehicles.
3, 2, 1, liftoff. Roger.
Intriguing electronic devices in which astronauts simulate spaceflight
Roger.
and develop proficiency in joining with another vehicle in orbit. And electronic data processing, which aids in the design of aircraft, spacecraft, and missiles, and serves commercial customers in a variety of ways. For the accomplishment of these challenges, McDonnell Aircraft has reinvested 81% of its cumulative earnings into facilities unique in its industry. An engineering campus that provides company engineers with an environment conducive to creative work. A polysonic wind tunnel, which tests at speeds of Mach 0.5 to 5.6. A hypervelocity impulse tunnel for testing at Mach 27. Space environmental simulation chambers of 32 inches, 5 feet, 8 feet, 18 feet, and 30 feet in diameter. A super clean area, about 3/4 of an acre in size, for spacecraft assembly and testing. And acres of floor area for production of aircraft and spacecraft. Products as complex as man has ever known. McDonnell Aircraft today is one of America's most exciting industrial firms, but to a company old-timer, not a whit more exciting than the early struggles which laid the foundation for the company's present-day success.
You know, sometimes it's hard to believe that only 25 years ago this was all there was to McDonnell Aircraft. And we had only the second floor at that. These buildings were our engineering buildings. We thought they were great. During the war years, we had factories all over St. Louis. We were in this old Cadillac building on Sarah and Laclede, We used to boast that we operated in the world's largest garage. In those days, we were doing subcontract work for several of the big West Coast aircraft companies. We had only about 5,000 employees, and half of them were women. We kept competing for prime contracts from the government right from the beginning. And finally, it paid off in September of 1941 when we received one for an Army Air Force bomber destroyer called the XP-67. It flew in 1944. I think it reached a speed of 400 miles an hour, which was pretty good in those days. This is the XFD-1, the Phantom 1. I guess we made a pretty good impression on the Navy because it was New Year's Eve 1942 that the Navy phoned Mr. Mack and asked if our company was interested in designing a jet fighter that could operate off an aircraft carrier. Our company was only 3.5 years old. Only one other jet airplane had ever been built in America, but we did it. We flew it in 1945. I remember the day it hit 500 miles an hour. We wired the Navy, and they were just as thrilled as we were. Of course, the big test didn't come until July 1946. There were some 3,000 people on the USS Franklin D. Roosevelt to watch Commander Jim Davidson take off in our Phantom from an aircraft carrier. A lot of the spectators didn't share our confidence. I have a recording of it.
The McDonnell Phantoms, on the WWII F-4, single-seat low-wing monoplane of conventional design. Over the Phantom furnished by twin axial flow lifting out several jet engines into the wing. Shot up against and there's signal to launch. It's shorty now, and you will really make me practice in front of our microphone here on the island of the Embark. Over into the air with about 150 to 200 feet to spare. An American naval aviation history has been made as a successful takeoff of an all-jet plane has been made from an American carrier. Here as he circles around, he's dropping down. He is getting a cut from the landing signal officer. He's dropping down onto the deck of the ship, catches his arresting cable, and falls to a stop just as quickly as does conventional type for a carrier aircraft. A beautiful takeoff, a beautiful landing by Lieutenant Commander James J. Davidson, making American naval aviation history as for the first time, an all-jet plane takes off, circles the carrier, and comes back into land.
And here's a snapshot of one of our first picnics. The kids loved it. We got to meet a lot of people. The last picnic I went to, there were some 25,000 employees and their families. And believe me, that's a pretty good-sized picnic. This is the F-2H Banshee. This was the second jet we designed. Note that this also had two engines. Our company always believed that the second engine was worth the extra cost because it added so much to the safety factor. And that's the way it has turned out. The Banshee was the only one of our aircraft to get into actual combat. It had a big role in the Korean War, mostly as a ground attack airplane in close support of troops. We also made a photo reconnaissance version of the Banshee. It was the first of 3 wreckings we built. We delivered nearly 900 Banshees. The Navy loved them. Not all of our airplanes, of course, went into production. This is an XF-85 Goblin, and we only made 2 of them. This was a great idea. It was an airplane which was designed to be launched from a B-36 bomber, go out and destroy attacking aircraft, and then return to its mothership. It worked, too. But it was still in the prototype stage when the B-36 began to phase out and be replaced by faster bombers. Then we got a contract from the Air Force to design and build this XF-88, a long-range fighter. Boy, were we delighted with this contract. This was really going to put us in the big leagues. We flew it at Edwards Air Force Base in California. It was fast and had plenty of range. Then one day we got the sad news. The Air Force didn't have the money to put it into production. But our company didn't give up. They spent a lot of money improving the design, and eventually it paid off. And in the meantime, we got an order to design the third in our series of fighters, the F-3H Demon. The Navy wanted a single-engine aircraft this time. Yeah, we had a lot of trouble with an underpowered engine for a while, but we bounced back. And the Demon became a good airplane. It was used in the Lebanon and Quemoy crisis in 1958. And the Navy used it for many missions: combat air patrol, bombing, strafing, so forth. Just about the time we first flew the Demon in 1951, the company bought from the city of St. Louis this big plant at the airport. The company paid about $10 million for the plant, which I think was more than we had earned in the 12 years we'd been in business. This must have been a big decision, but there's no doubt it paved the way for our subsequent growth. One condition of this purchase was that the money the company paid be spent on airport improvements only. The year after we moved into our new plant, the Air Force finally decided to place a production order with us for that XF-88. But by that time, we had designed a supersonic plane, and we wanted the Air Force to buy it. This was a risky business because we knew it might open the door for a new competition, and we might lose the business entirely. But the Air Force finally bought our proposal, and we started work on the F-101 Voodoo. This is a great airplane.
The F-101 Voodoo, a great airplane indeed, and one whose achievements will live long in the memory of the men and women of McDonnell who designed and built it. The F-101A Voodoo, the long-range fighter-bomber which set the world speed record of 1,207 miles per hour in Operation Firewall in 1958. The RF-101 Reconnaissance Voodoo, which in Operation Sunrun raced from Los Angeles to New York City in 3 hours 7 minutes and completed the round trip in 6 hours 46 minutes. The F-101P, two-place interceptor for the Air Defense Command. The F-101 Voodoo, the first supersonic aircraft to carry nuclear weapons. The first aircraft to be exposed in flight to an H-bomb explosion and then return safely. And in October 1962, an aircraft that flew scores of missions at treetop level over the island of Cuba, bringing back vital photographs that revealed the Soviet missile buildup only 90 miles off our shores. The F-101 Voodoo, a great airplane indeed.
Although fighter aircraft has been our principal business during the year, we've had a lot of activity in other fields. Here's a good example: the XV-1 converter plane that we developed for the Army. Now, as you can see, it operated like a helicopter. Then it went into horizontal flight, hitting speeds of 200 miles an hour. This was a research vehicle. We made only 2. We had previously done a lot of development work on helicopters. We made the world's first ramjet helicopter. We called it Little Henry. We made the world's first twin-engine helicopter. We called it Whirlaway. And we made a flying crane, which for a little fella carried a lot of weight. We've been in the missile business too since 1943 when we started work on the gargoyle, a guided bomb. Later we built the Katydid, a target drone. For the past 13 years, we've been producing the airframe and ramjet engine of the Navy surface-to-air Talos. Our biggest missile program was the Quail missile for the Air Force. Now, this was a complex piece of hardware to produce. We had a lot of people working on it, and we did practically the whole job, including the support equipment and the launch system. The Quail is a unique missile in that it has no warhead. It's strictly a decoy. The Quails are launched in coveys by B-52 bombers. Because they fly at the same speed and altitude of the bomber and create the same blip on an enemy radar, the enemy can't distinguish the bomber from the harmless Quails. Still working on another missile concept which I think has good possibilities. An aeroballistic missile which flies within the atmosphere at hypersonic speed. We launched 3 of these from Cape Canaveral in 1959. In addition to our missile, we also make an asset glide re-entry vehicle which flies at hypersonic speeds. Now, this is an extremely interesting product. In the first place, it's made out of so-called exotic metals which are terribly hard to fabricate. Secondly, we get some very valuable data on re-entry by winged space vehicles. Asset was first launched at the Cape in 1963. It traveled 11,000 miles an hour and landed right on the button. And now we come to the Phantom II. We were in real tough competition for this airplane, and it meant an awful lot to us, and for that matter, to St. Louis. It was a big day when we won it. We would have had to lay off 6,000 people if we lost this competition. You know, some people seem to feel that government contractor gets its business on a platter. Nobody better suggest it to anyone who was in on this competition. The Phantom was christened with considerable difficulty. The bottle would break by Mrs. Bethel Milne, wife of the Secretary of the Navy. She was a good sport. They finally popped the cork. I guess you know this Phantom is some airplane. Well, you ought to see it take off. It flies at approximately 2.5 times the speed of sound, and has flown to altitudes in excess of 100,000 feet. All in all, it established 15 world speed records. It set a world speed record of 1,606 miles an hour. It set a 3-kilometer record of 902 miles per hour at a reach of only 125 feet above the ground. How do you like that? Navy pilots flew it from Los Angeles to New York in 2 hours and 50 minutes. And it set 8 time-to-climb records. Listen to this. From a dead stop, it went down the runway, took off, and flew 7.5 miles high in 1 minute and 17 seconds. But the surprising thing about the Phantom is the fact that it also can slow down to 130 miles an hour for landing on a carrier or for a short runway. Now, this is important when it's used to support ground troops. You probably gathered that the Phantom is a very versatile aircraft, and you're right. Because of this, it's now in service with the Navy, Marine Corps, and Air Force, and that's a rarity. The true measure of the airplane, of course, is its capability for combat. For one thing, it can fire missiles at enemy aircraft or against ground targets. It can deliver conventional bombs. or it can streak into its target below the level of enemy radar detection to deliver nuclear bombs. The military call it the best aircraft of its kind in the world.
And so we would be up to date on the McDonnell story had it not been for an announcement by the newly formed National Aeronautics and Space Administration in Washington on January 12, 1959. McDonnell Aircraft was awarded a contract to design, develop, and construct the nation's first manned spacecraft for Project Mercury. Time magazine called the award a payoff for pioneers, and indeed it was. For McDonnell engineers had been working on the concept of a manned spacecraft with company funds for more than a year prior to the award. When NASA asked for proposals, a McDonnell team was ready. Work started immediately. In 2 months, a mock-up had been built. Fabrication of the spacecraft began. And then came testing, more testing than had ever before been given a manned vehicle. The first manned spacecraft was delivered in December 1960, only 23 months after the company had received the contract. Now the suspense was building up. The eyes of the entire world were focused on the little McDonnell product. The company's prestige was on the line. Each member of the team sensed it. Finally, it was May 5th, 1961. Astronaut Alan B. Shepard was blasted into space by a Redstone rocket. Some 15 minutes later, America's first manned space venture was pronounced a success. 2 months later, astronaut Gus Grissom flew a similar mission, and America was ready for orbital flight. It was February 20th, 1962, that John H. Glenn entered his spacecraft, mounted atop a huge Atlas rocket, for his historic adventure. By mid-morning, he was on his way. At a speed of 17,544 miles per hour, he circled the Earth 3 times. 4 hours and 38 minutes later, he was safely down in the Atlantic. In the space race, America was catching up fast. John Glenn wasted no time in returning to the plant where his spacecraft had been built. Mr. Mack summoned the team.
This is Mac calling all the team. We are gathered here around our Mercury spacecraft number 13, a number now full of meaning for our team. Number 13 came home to St. Louis last night. Number 13 came home, but only to stay briefly, because she has now made history, and under her christened name, Friendship 7, has lifted up.
He paid his tribute to company personnel and to NASA, and he introduced John Glenn.
Turn this hardware into the glorious Friendship 7 Epic of America. It was the superb pioneering astronaut who breathed the spirit of America into this vehicle as he rode her, subdued her, and brought her home with masterful skill. Therefore, joyous we are today to have with us John Glenn, who stands here representative of the 7 astronauts for whom Friendship 7 was named.
Yeah.
This astronaut, this great American, needs no introduction to you.
Mr. Mack paid special tribute to all the engineers. With all due respect to all the engineers, it took a lot of you that I'm looking at here today to put the actual hardware together. And I know that the way it was put together and the way the mission worked out, there was more went into it than just a wage that you were earning here in the plant. Your hearts went into it as ours did down at the Cape, too. For that, I thank you very much.
Astronaut Scott Carpenter duplicated Glenn's 3-orbit mission 3 months later. Ole Schirra flew a nearly perfect 6-orbit flight in October, parachuted safely in the Pacific Ocean in full view of those on his waiting aircraft carrier. Finally, there came a fitting climax to the great adventure. On May 15, 1963, astronaut Gordon Cooper was rocketed into space for a 22-orbit, 580,000-mile journey around the Earth, consuming 34 hours, 19 minutes, and 47 seconds. Before landing only 4 miles from the USS Kearsarge.
Personnel, this is Mac calling all the team. Our little aerospace company has a new high today. We are honored to have with us the President of the United States. Many of our teammates here know...
McDonnell workers watched and listened intently as Mr. Mack shared the historic occasion with them.
In going into space as a means of peaceful competition and a way of finding wonderful and creative substitutes for war while giving release to the competitive spirit of mankind. I present to you the President of the United States.
Mr. McDonnell, Senator, Governor, Mr. Mayor, I want to express my very warm thanks to all of you. I know that some of you are on the first shift, and some on the second shift, and I appreciate very much your coming out and saying hello. This is a most important effort in which you're all involved, building these planes which help protect the security of the United States and the dozens of countries which are associated and allied with us all around the world, which would not be free if it were not for the power and the determination of the United States.
The President explained to an appreciative audience that it was essential that the United States be first in space. And then to the McDonnell team came the ultimate in praise for a job well done.
And I can imagine no
The FA-18. Combining the speed and agility of a fighter a marvel of modern aircraft design. It's every pilot's dream to fly one. From a training field to the carrier deck, the F-18 has seized center stage as the world's elite strike fighter, the backbone of carrier-based aviation. Every day, in the skies over hostile territory, squadrons of F-18s are on the prowl. This is the front line, where the F-18 excels. Striking targets in support of troops on the ground and tracking the horizon for enemy fighters. These jets project power from thousands of feet in the air, and their reach extends to almost anywhere on the planet. For the F-18, home base is a floating runway churning the waters miles offshore. This is one of the United States' 12 aircraft carriers, a fully functional airport at sea. Even after striking targets and risking the threat of enemy fire, these F-18 pilots can't rest until they bring their aircraft safely to a stop on board. A carrier air wing is made up of more than just fighter jets. Each of the 80-plus planes on board carries out a specific task. S-3 Vikings for refueling and sub-hunting, E-2C Hawkeyes for reconnaissance, EA-6B Prowlers for jamming enemy electronics, and HH-60 Seahawk helicopters for shuttling people and materials. All these aircraft and the carrier itself are focused on one objective: forward force projection. The F-18 Hornet is a $38 million high-tech machine. It's the smallest plane on the carrier, just 56 feet long and 15 feet tall, with a 40-foot wingspan. Its streamlined design is characterized by a long, narrow fuselage and side-by-side powerful twin engines. At 21,000 pounds, it weighs half as much as many other fighter jets, with an advanced composite airframe of aluminum, titanium, and steel. To fly one of these jets is to join the ranks of just over 1,000 active Navy and Marine Corps Hornet aviators. The journey to become a carrier-qualified F-18 pilot begins thousands of miles away from hostile territory, in the peaceful farmland of Central California. Naval Air Station Lemoore is the Navy's newest and largest master jet air station. The flat terrain and lack of neighbors makes Lemoore a perfect spot. Here, aviators who have passed their basic flight training learn how to fly the F-18. It's a mentally and physically challenging program. The newest class of trainees will undergo 300 hours of classwork and at least 300 hours more in simulators and training aircraft before they can even step into the cockpit of an F-18 jet. Lemoore's Flying Eagles of VFA-122 are among the best in the Navy when it comes to training elite aviators, preparing them for battle. To forge elite pilots out of raw aviators, trainers here push their students harder than most other squadrons. Since the delivery of the first F-18s in 1980, Lemoore has been known as the home of the Hornet. Nearly 365 days a year, from the early morning on, the skies over Lemoore echo with the deafening roar of F-18 jet fighters. The F-18 that these trainees hope to fly is a much more sophisticated machine than burlier Navy jets. During the 1960s and 70s, the Navy was launching two formidable workhorses from its aircraft. The F-4 Phantom was a reliable, fast, powerful fighter designed for air-to-air combat. The A-7 Corsair was a slower armored jet, a lethal night bomber that could deliver a 15,000-pound payload. Combined, the two planes flew hundreds of thousands of combat sorties, military operations all over the world. But by the mid-1970s, the F-4 and A-7 were aging and nearing the end of their useful lives. The Navy needed newer, higher-tech aircraft able to handle the demands of modern warfare. The Navy conceived of the FA-18 in order to replace both the F-4 and A-7 in one combined strike fighter design and thereby free valuable space on its aircraft carriers. As a result, the FA-18 is the first jet designated both S for fighter and A for attack. The deployment of a multi-role strike fighter had been a long-time goal for the Navy, and the FA-18 has fulfilled that goal and more. While past planes like the F-4 could be configured as neither a bomber or a fighter for a single mission, the FA-18 can fill both roles simultaneously. The FA-18's multi-role capability has made it the mainstay of the carrier air room. And like all Navy planes, it still has to meet the tough requirements of fleet aviation. On the deck of an aircraft carrier, FA-18s undergo constant structural stress caused by the violence of landing. Landing an FA-18 is the equivalent to bringing a loaded semi-trailer from 150 miles per hour to a full stop in less than 3 seconds. The FA-18 is also built to sustain a punishing takeoff. Powerful engines, General Electric's F-404s, are each capable of generating 18,000 pounds of thrust, an astounding 1/4 of the thrust of the rocket that sent the Mercury spacecraft into orbit. The FA-18's twin engines have built-in redundancy. Despite all the extra weight needed to land, launch, and keep the FA-18 aloft, its power and small size make it the most maneuverable aircraft in the Navy's airborne arsenal. Racing at top speeds of Mach 1.8, leading-edge wing extensions and outward canted tail fins stabilize airflow, while the wide range of motion in the ailerons, flaps, and tail planes give the Hornet unparalleled pitch and roll control. The FA-18 is so maneuvered, it's the jet of choice for the Navy's Blue Angels demonstration squad. These daring pilots have been flying the FA-18 Hornet since 1986. The jet's speed and handling characteristics have allowed the team to add new maneuvers to their program. The FA-18 can turn on a very tight radius and perform rapid rolls, all while also displaying the best slow-speed ability of any Navy jet. But the Hornet's maneuverability takes a physical toll on the pilot. Its high-speed turns can create over 7.5 Gs. Under this stress, the average pilot feels almost 1,500 pounds of downward pressure on his body. To prepare for the rigors of flying an FA-18, pilots at Lemoore Naval Air Station undergo intense training. One of the most grueling stages takes place in the centrifuge. To maintain control during the most difficult maneuvers, the FA-18 contains a computer-assisted fly-by-wire system. Some pilots say it makes operating a plane more like a video game than traditional flying, but its impact on safety and handling is very real. If the pilot does lapse into G-lock during a maneuver, the FA-18's flight system takes over, automatically leveling out the jet's path through the air. This highly advanced flight system is just one of the striking contrasts between the FA-18 and other carrier-based fighters past and present. Perhaps the most legendary was the F-14 Tomcat. In speed, range, and sheer muscle, the F-14 is unmatched in naval aviation history. This fast, powerful jet was known as the King of the Carrier Deck. Compared to the Tomcat, the smaller, leaner Hornet almost looks fragile. Since its first deployment, this powerful jet has flown thousands of successful combat missions. One of the F-A-18's greatest strengths is its reliability. The F-A-18 contains 50% fewer parts than the F-14. And fewer parts means the plane is easier to maintain. One floor down from the flight deck is the hangar deck. This is where planes go when they are in need of work. Off the hangar deck, crews specialize in getting grounded planes back into action. The F-A-18 has proven even more dependable than the Navy hoped, especially when compared to the F-14 Tomcat. Tomcat maintenance squads must work almost 4 times as many hours to maintain their aging aircraft. When not undergoing repairs or routine maintenance checks, carrier-based F-A-18s are either in the air or parked, wing to wing, on the flight deck. With as many as 80 planes aboard, and several at a time taking off or landing, the flight deck can become dangerously busy. F-A-18 pilots rely on experienced flight deck operators to move their planes from one spot to the next. With the amount of activity on the flight deck, pilots and personnel have to be under constant alert. With all the heavy moving parts, one wrong turn can spell disaster. F-A-18 pilots have to make sure they're constantly on the same page with their operators, communicating with them using a strict system of signals. To make room on the crowded deck, all naval planes, including the F-A-18, are designed to take up as little space as possible. With $38 million worth of machine under their control, the operators gently ease the F-A-18s into their spots. Once in place, another crew chocks the wheels and chains down the plane. They're all following a well-ordered parking plan, a plan monitored just off the flight deck. The handler keeps track of the plane's position and uses a complicated set of push pins and buttons to update each plane's status. The aircraft templates are exactly to scale, even down to the area a helicopter's props take up when spinning. Precision like this is essential, as the slightest miscalculation in timing or aircraft size could cause a deadly mishap. One of the most important jobs is to monitor when a jet is low on fuel. Before an F-A-18 can be cleared for launch by the handler, its tanks have to be filled. Fueling and defueling the jets is a specialized task handled by a meticulously trained crew. And they're kept busy with the F-A-18s, which consume massive amounts of fuel, also known as JP-5. One criticism of the F-A-18 is that it has a relatively small onboard fuel capacity of 1,600 gallons. To increase its range, it can carry 3 external tanks. Including its internal tanks, the F-A-18 carries roughly 2,500 gallons of JP-5. On a regular patrol, it can use almost all its fuel in just an hour and 45 minutes. The blast from an FA-18's afterburners is so hot, the protective jet blast diffractors on the flight net are made of reinforced concrete, as metal would simply melt. To keep the FA-18's hungry engines well fed, the carrier needs to keep a large supply of JP-5 on hand. There's so much fuel on board, it serves as ballast to steady the ship and keep the flight deck level. Over a 6-month period, a carrier's planes can burn through almost 12 million gallons. To keep the jets fully fueled, the carrier rendezvous with a supply ship every 7 to 10 days. Fully fueled and operational, a carrier's F-18 squadrons can fly over 100 sortings per day. On mission, or as pilots say, in country, the first order of business, or FA-18s, is to defend against air-to-air targets. This is what's known as dogfighting, and it's an arena in which the FA-18 has proven highly successful. Close combat is a modern duel to the death, and dogfight training is among the most intense stages of learning how to fly the FA-18. The dogfighting stage marks roughly the halfway point in FA-18 training, combining what trainees learned in class with high-G maneuvering. This is also the time when new pilots first challenge their instructors. Their game faces on, teacher and student prepare to square off. Before takeoff, the pilots personally ensure their jets are in working order. For the high-speed maneuvers of dogfight, pilots need to be certain their jet will perform flawlessly under even the heaviest G-forces. All flaps, ailerons, and stabilizers are tested. The dogfighters taxi out, and the duel begins. When they're on the offensive, pilots need to stay on the tail of their adversary and lock on target. Offensive maneuvering requires severe G-turns and sudden escape modes. In the last exercise, the trainee proves his mettle, turning the tables and getting on his instructor's tail. Among the FA-18's most lethal air-to-air weapons is the Raytheon AMWAM, or Advanced Medium-Range Air-to-Air Missile. Pilots fire and sometimes even steer these weapons from the FA-18's cockpit. What makes these weapon systems all the more lethal is a cockpit design with a heads-up display that allows the pilot to perform many functions without looking down. And almost every task a pilot needs to perform can be done without having to take his hands off the controls. With the FA-18's advanced cockpit design and fly-by-wire control system, the pilot has more flexibility than in any other Navy jet. To get this comfortable with their planes, future FA-18 pilots spend over 50 hours in a flight simulator at NAS Lemoore. It recreates almost exactly the cockpit and flight characteristics of the FA-18. This state-of-the-art equipment enables aircrews to virtually fly every scenario. The final test that future Hornet pilots face in the simulator prepares them for one of the most difficult tasks in naval aviation. After simulated carrier landings, pilots got even closer to the real thing. This is Lemoire's landing signal area, complete with arresting cables, distance markers, and even the identical landing lights pilots use as a guide to touch down on the carrier successfully. The runway at Lemoire's Reeves Field stretches for 13,500 feet, giving pilots plenty of landing room. On a Nimitz-class carrier, the landing strip is just 500 feet long. To bring an FA-18 to a complete stop, the pilot has to grab or trap one of 4 arresting cables. Without some sort of arresting device, the jet would skid right off. Dropping 800 feet in just 15 seconds, pilots have to keep the plane's nose up and maintain the correct attitude or angle of descent. Flying in at a minimum of 150 knots to avoid engine stall. As soon as he touches down, the pilot revs his engine in case he slips the wire. If he misses, he takes off, circling around to try again. During the day, the pilot can at least see the deck. At night, the carrier turns off all but a few lights to avoid becoming an easy target for enemies. Liquid vapor torches cast just small pools of light. The rest of the flight deck remains as dark as possible. From 3 miles away, the carrier looks like a pinprick of light. There's no way to tell which direction it's moving, and the fatigued pilot's eyes can easily play tricks on him. Pilots returning at night have often been aloft on missions as long as 6 hours. Day and night, FA-18s and other planes are watched closely in the Air Traffic Control Center, a miniature version of what exists at any major airport. At the very top of the tower, the air boss directs the landings and takeoffs. His assistant, the mini-boss, oversees the front, where the 2 most active catapults are. All information about the carrier's FA-18s from launch to landing goes through the air boss. It's his job to deal with information, occasionally jotting notes on the wall and windows to keep it straight. He then relays the critical information to wherever it needs to go. The air and mini-boss are both aviators. This way they know every procedure intimately and immediately understand the pilot's status. Even the captain of the carrier is an aviator, highlighting the role of the aircraft carrier as a floating air base. The FA-18's central role on the carrier is clear from the top of the tower to deep into its belly. This is one of the ship's 40-plus weapons magazines, where crews prepare the FA-18's various weapons loads. This 1,000-pound ordnance is a dumb bomb, just one weapon in the FA-18's arsenal. The FA-18 can be configured to carry over 24 different bombs and missiles. Once the FA-18's bombs are assembled, they ride a series of elevators to the flight deck. Here, the ordnance comes under the control of weapons inspectors. They wheel the bombs over by hand before attaching them to the FA-18's pylons. For all the high-tech gadgetry surrounding the FA-18, some tasks still come down to raw muscle power. Although the bomb is not yet armed, it does contain almost 1,000 pounds of explosives, In past carrier disasters, fires had ignited the aviation fuel, which then set off the bombs. Today's bombs had extra insulation so that they can withstand short periods of extreme heat or fire. The last step is to add the fuse. The final arming of the bomb takes place only after the plane takes off. From inside the F-18 cockpit, pilots throw a switch, activating them. Dumb bombs are just a small part of the F-18 strike-ready arsenal. For precise ground support, they include the latest laser and GPS-guided weapons. One of the F-18's most lethal air-to-ground weapons is the JSOW. A large precision strike weapon, the JSOW affixes to the F-18's middle wing weapons station. Once launched, it releases two wing structures that allow the missile to glide toward its target. Skimming just a few feet above the ground, the JSOW releases powerful cluster bombs that can destroy multiple targets in one strike. Equally lethal, but with different capabilities, is the HAR, or High-Speed Anti-Radiation Missile, as well as a host of guided and unguided bombs. Flying missions over remote testing areas, pilots take full control of the F-18's precision strike capabilities, pinpointing designated targets and releasing fully armed bombs. What makes the F-18's weapons so lethal is the latest in targeting technology. Carrier-based Hornet squadrons increasingly employ deadly accurate infrared systems. F-18s also track targets using highly advanced radar technology, housed in the nose of the planes. These unique systems allow the pilot to switch between air-to-air and air-to-ground modes with a push of a button. Integrated into an electronic network, the F-18 takes on a central role in frontline operations. Through satellite data link, the radar, map, and weapons displays of the F-18 cockpit can be seen by fellow aircrew, as well as commanding officers in the carrier strike group. And with each updated model, the F-18 grows more sophisticated. At Lemoore, the latest class has spent 9 months preparing for battle. As they set out for the fleet, the most recent graduates take control of the next generation of F-18. The Super Hornet design is based on the original F-18, but it is an even more lethal machine. The Super Hornet is being modified to fill almost every role on the carrier, from electronic jamming to refueling. The carrier air wing of the future will be made up of a lethal and effective team. The F-18 will be defending the skies for decades into the future.
The design of the McDonnell Douglas F-4 Phantom II has surpassed 60 years. Initially intended for carrier-based operations, it swiftly evolved into one of the most significant land-based tactical aircraft in the Western world. Over 5,200 Phantoms were manufactured, and today they continue to serve in Greece, South Korea, Turkey and Iran. Originating in the early 1950s as the McDonnell AH-1 supersonic attack aircraft, it transitioned in May 1955 into the F-4H-1 two-seat fleet defense fighter. With its Mach 2 Plus performance, the F-4 boasted an armament featuring 4 Sparrow air-to-air missiles, semi-recessed in the lower fuselage and complemented by a robust search and fire control radar. Thus, the F-4H emerged as the world's first fighter equipped with self-contained search and destroy capability. On May 27, 1958, the XF-4H-1 prototype made its debut at Lambert Field in St. Louis, with test pilot Bob Little at the controls for its inaugural flight.
Our intention on that flight was to take the airplane supersonic on its first flight. We had done that 4 years before in the F-101, and it was certainly something to be accomplished in the F-4. It didn't work out that way. The landing gear didn't come all the way up. And on that flight, a hydraulic system failed on takeoff, so I had to bring the airplane in after about 20 minutes of learning how to fly it well enough so I could land it.
Despite encountering challenges during its maiden voyage, as the XF-4H taxied alongside examples of McDonnell's other major fighter program of the period, the F-101 Voodoo, it became evident that the company had a triumph on its hands. The narrative of the Phantom also encompasses General Electric, which supplied the J-79 turbojet engine. In 1951, the company embarked on developing a new axial flow engine that aimed for low weight and excellent fuel efficiency at Mach 0.9, while still possessing the strength and thrust for Mach 2 performance. To accomplish this, the J-79 incorporated innovative design elements, notably the variable stator compressor with adjustable blades and an afterburning exhaust nozzle essential for lightweight and optimal performance at very high speeds. This nozzle utilized secondary air to regulate the expansion of the primary exhaust, also serving to cool the engine, thus obviating the need for costly metallurgical solutions. Mechanically interconnected, 2 sets of nozzle fingers dynamically adjust, opening and closing to shape the exhaust for optimal balance between thrust and fuel consumption across the engine's entire operating spectrum. This innovation results in a substantial 2/3 boost in thrust, albeit at the cost of exorbitant fuel consumption. The full-scale variable stator compressor unit underwent its inaugural test in August 1953, yielding performance figures so impressive that the test crew initially suspected instrumentation malfunction. At much the same time, the afterburner was connected to a J-73 turbojet and tested with encouraging results. The integration of the afterburner with the J-79 engine culminated in the complete new engine's placement in the test cell by June 1954. Approximately 150 hours of testing on the J-79 was supplemented by an additional 800 hours on the J-73 for further evaluation. A pivotal moment in the test program occurred with the inaugural field run of the J-79 engine. Upon ignition, the test crew promptly scrutinized the instrumentation. Subsequently, with the engine throttled to idling speed, ground and flight test engineers meticulously inspected it for any signs of fuel or oil leaks and other potential failures. Once this initial examination was cleared, the engine underwent higher speed testing before being shut down. In May 1955, the groundbreaking new engine took flight, housed in a nacelle beneath the belly of a converted North American B-45 bomber. Historic footage captures the modified B-45's ascent on May 20th, 1955. After the B-45 achieved stable flight, the J-79's nacelle was extended, facilitating initial test runs to confirm its capabilities in steady, level flight. Subsequent tests included air starts, essential for any advanced engine. The J-79's performance was thoroughly assessed across various flight conditions, proving its mettle with afterburning thrust ratings of up to approximately 13,000 pounds. The inaugural flight-worthy J-79 was transported across the United States to Edwards Air Force Base in California, where it underwent unpacking, ground testing, and installation for flight trials. This process proceeded smoothly, with fuel, oil, and over 100 electrical connections established without major issues. The XF-4D-1, a prototype of the high-performance Naval Interceptor Skyray, was selected as the test aircraft for the flight trials. Ground runs were conducted at both dry and afterburning thrust levels to validate the fundamental installation. On December 8, 1955, under the command of test pilot Roy Pryor, the aircraft equipped with the J-79 engine embarked on its maiden flight. Taking off downwind to maximize runway utilization, the aircraft required approximately 6 miles of the renowned dry lake bed at Edwards, formerly known as Murrock, until 1950. The flight encompassed a climb to 18,000 feet before safely returning for an evening landing. The entire flight operation exemplified successful flight testing. The J-79 was soon cleared for operational service, and early examples of the type were installed right from the beginning of the Phantom's production run. By the late 1950s, the Phantom's prominence surged following the placement of its first production contract in December 1956. This overview of an F-4B naval model, temporarily loaned to the US Air Force, highlights the aircraft's key attributes. Positioned at the front is the pilot, with the radar officer seated behind. A ladder, visible inside the rear canopy, can be deployed to darken the cockpit, ensuring optimal conditions for viewing the radar screen. Despite being relatively spacious and conventional for the era, the cockpits are well equipped with displays and controls. Occupants are seated on Martin Baker Mark V ejector seats, engineered for safe ejections even at zero altitude and speeds as low as 150 miles per hour. Mach 2 performance is facilitated by the 2 fully variable ramp inlets for the J-79 engines. A splitter plate diverts the boundary layer of the slower moving air close to the fuselage, while the inlet ramp adjusts at speeds exceeding Mach 1.4 to regulate the shock wave pattern, ensuring an uninterrupted airflow into the engine. This system operates automatically, controlled by the aircraft's air data computer. Notably, Navy and Air Force Phantoms typically feature distinct tyre configurations. Both types of tyres boast the same diameter, but the Air Force variant, depicted on the left, showcases a broader design. This broader tyre offers an increased touchdown area, allowing it to be inflated to lower pressures, suitable for operations on the extended runways typically available to land-based aircraft. Positioned on the port side of the fuselage is a pneumatically extended ram air turbine, serving as an emergency power source to sustain essential systems in the event of engine failure. Operating down to a speed of 225 miles per hour, the turbine supplies electrical power, transitioning to hydraulic power for the landing systems thereafter. The centerline hardpoint for Stores Sidewinder Tactical Optical Recognition Carriage is augmented by 4 substantial pylons situated under the wings. Along the leading edges of the wings are 3 section slats designed to maintain an even airflow over the wings and reduce stalling speed. This feature's efficacy hinges on boundary layer control, achieved by tapping air from the engine compressor and venting it through the depicted slots. This is one of the 2 trailing edge flaps, which are also fitted with boundary layer control. Similar to the leading edge system, these slots direct air tapped from the engines over the upper surface of the flap. This airflow manipulation enhances the effectiveness of these relatively small surfaces. The flaps have a maximum deflection of 60 degrees, with full flap setting employed during landing and half flap setting for takeoff. Lateral control is achieved through a combination of spoilers and ailerons, with spoilers utilized at high airspeeds and ailerons at low airspeeds. Each wing's underside features a hydraulically operated speed brake, enabling rapid deceleration from speeds as high as Mach 2.4 at any flight altitude without inducing buffet or altering pitch trim. Although extending the speed brakes during landings is safe, their effect is minimal at low speeds. The elongated low vertical tail addresses headroom constraints on US carriers' hangar decks and incorporates a powered rudder for yaw control. Beneath the powered rudder lies the vent for the fuselage's complex of 6 fuel tanks. The slab tailplane halves ensure complete pitch control under all flight conditions and are angled downward at 23 degrees to enhance directional stability by augmenting the effective side area of the rear fuselage. Positioned between the J-79 tailpipes is the arrestor hook, typically housed beneath the rear fuselage fairing but deployed during carrier landings. This feature, retained on land-based Phantoms as well, has proven invaluable for achieving short landings on runways equipped with appropriate arrestor gear. Crafted from a special high-strength alloy, the hook is engineered to withstand the immense forces encountered during arrested landings. Heat resistance in the rear fuselage is enhanced through the utilization of stainless steel, titanium, and ram air cooling. Located at the far end of the tail is the compartment for the 16-foot braking parachute, essential for reducing landing distances on standard runways. The aperture in the tail facilitates the exit of cooling air, intentionally drawn into the rear fuselage structure above the engine exhausts. Renowned for its distinctive appearance, the Phantom has always stood out in the realm of aviation aesthetics. One of these distinctive features is the power folding of the outer portion of each wing, normally angled at 12 degrees. The folding system is engineered to reduce the Phantom's width for ease of movement on carrier decks and elevators. This feature, retained on land-based Phantoms as well, has demonstrated its practicality in various operational scenarios. With the wings folded, the internal plumbing for the boundary layer control system becomes visible. The sizable nose radome accommodates the 32-inch diameter antenna of the APQ-72 main radar. Positioned beneath the nose is the fairing for the infrared scanner, serving as a backup target acquisition capability should the main radar encounter jamming or failure. The Phantom entered operational service with the US Navy in 1961, prompting rapid conversion of squadrons from older aircraft types to equip the Navy's formidable carrier force. The section illustrates key elements of carrier-borne operations, featuring F-4Bs from Fighter Squadron 74 aboard the USS Forrestal, the Atlantic Fleet's inaugural Phantom unit, also known as the Bedevilers. Prior to each mission, a meticulous briefing sets the stage, followed by flight crews donning survival equipment on top of their flight suits. Upon the command from flight operations, crews proceed to their designated aircraft. Meanwhile, deck crews, distinguishable by different coloured vests for identification, finalise preparations for the mission launch. The pilot conducts a thorough walk-around check of the aircraft before both pilot and radar officer embark on the Phantom. The launch weight is indicated for the catapult officer's attention. In the fleet defence role, the pilot assumes control of the aircraft and oversees combat operations, while the radar intercept officer manages radar operations and initiates early interception procedures. Subsequently, both cockpit canopies are sealed shut, and the deck crew raises the catapult bridle in readiness for launch. The flight deck director meticulously guides each aircraft into position over its assigned catapult, carefully manoeuvring it onto the shuttle over the wheel section of the catapult. Subsequently, the bridle is securely attached, and any slack in the bridle is eliminated by nudging the catapult shuttle forward slightly. Simultaneously, the companion Phantom on the second catapult undergoes identical preparation, with cockpit checks also finalised. The deck director signals the pilot to advance the engines to takeoff power. Finally, the director signals the launch, and the Phantom is hurled down the catapult run and over the bow of the carrier at a speed of 185 miles per hour. As the first pair embarks on their combat air patrol, another duo of Phantoms taxis towards the launch area. Upon reaching the designated spot, deflectors are raised to redirect exhaust gases away from the flight deck. Simultaneously, the shuttle is repositioned, allowing the next Phantom slated for that catapult to align its nose wheel unit over the shuttle and position itself in line with the catapult while the deck crew raises the bridle. This launch sequence continues with up to 4 aircraft dispatched almost simultaneously. Additional aircraft are brought up via the deck edge elevators. Enabling launches to proceed, including instances of triple dispatchers. Equipped with a 2-person crew, potent radar, and an arsenal comprising Sparrow medium-range and Sidewinder short-range missiles, the Phantom was heralded as the world's first fighter with independent search and destroy capability, free from ground control, and proved invaluable for the US Navy in the 1960s. Its service capabilities were swiftly showcased through a series of world records. In December 1959, the Phantom achieved a zoom climb-to-altitude record of 98,556 feet. In September 1960, it secured 2 closed-circuit records at speeds of 1,217 and 1,390 miles per hour. Less than a year later, in August 1961, it established a low-altitude speed record of 903 miles per hour, followed shortly thereafter in November by an absolute world speed record of 1,606 miles per hour. Undoubtedly, one of the most remarkable early achievements took place in May 1961, commemorating the 50th anniversary of naval aviation. 5 prototype Phantoms embarked on a journey from west to east across the United States, completing the Transcontinental flight in a mere 2 hours and 47 minutes, smashing previous records. Upon concluding their patrol, the Phantoms returned to the carrier for landing. Approaching at 150 miles per hour, each aircraft undergoes visual inspection to verify the lowering of landing gear and flaps. They're then guided down by the landing signal officer once the assistant confirms a clear deck. As the pilot aligns for approach, guidance is provided by an amber light known as the meatball, situated on the right side of the flight deck. The pilot keeps this lined up with the row of green lights to ensure that he is in the groove, the correct glide slope to fly the aircraft onto the deck and catch the wire. Different light angle approach settings are configured for each type of aircraft aboard. Following each landing, the wire disengages from the arrestor hook and returns to its position as the landed aircraft taxis clear, facilitating the prompt arrival of the next aircraft. Subsequently, the landed aircraft are lowered to the hangar deck via the 4 deck edge elevators to initiate the maintenance cycle before their next mission. Each of the 4 Forrestal-class ships boasts approximately 3.5 acres of maintenance area below the flight deck, though this capacity accommodates only half of the carrier's 90 aircraft at any given time. Throughout the 1960s and early 1970s, both the F-4B and the upgraded, more potent F-4J versions of the Phantom served as the backbone of the US Navy's air defense. Extending outward to a radius of 400 miles from the carrier, the Phantom maintained unrivaled effectiveness in combat air patrol until the introduction of the Grumman F-14 Tomcat. During the Vietnam War, US Navy Phantoms occasionally operated as attack aircraft from land bases while detached from their parent carriers. These F-4J aircraft, derived from the original F-4B, featured more powerful engines, drooping ailerons to complement the flaps, slotted and hence more efficient tailplanes, and an enhanced combination of AWG-10 fire control radar and AJB-7 bombing system for improved air-to-air and air-to-ground capabilities. The pilot assumes the primary responsibility of flying the aircraft, remaining fully engaged in ensuring all systems are functioning optimally and monitoring fuel levels while maintaining a vigilant visual scan of the sky for potential threats that may have eluded radar detection. In the rear seat, the radar intercept officer employs increasingly sophisticated equipment to monitor the tactical situation and provides ongoing updates to the pilot. The Phantom earned its stripes in Vietnam and remained one of the few US combat aircraft in that theatre never to be withdrawn. Throughout the conflict, it consistently demonstrated its ability to meet the diverse demands placed upon it and garnered deep admiration from its crews. However, the Phantom wasn't without its shortcomings, particularly in its early iterations. One notable flaw was its smoky power plant, which could inadvertently reveal the aircraft's position to adversaries. Another significant operator of the Phantom in Vietnam was the US Marine Corps, with a key Marine Aviation unit, Aircraft Group 13, stationed at Chile in 1968. Aircraft were stored in blast-proof revetments between missions to mitigate the impact of communist rocket and mortar attacks on airfields and to impede potential close assaults by Viet Cong sappers. Prior to boarding the Phantom, the crew conducts a thorough walk-around check to ensure the aircraft exhibits no visible defects. They inspect the underwing pods to confirm full attachment, complete loading, and proper electrical connection, as well as to ensure the safe handling of the 2.75-inch rockets. Examination of the main landing gear wheel well is conducted to detect any signs of hydraulic or fuel leaks. A brief inspection confirms that the Mark IV 20mm cannon pod is loaded with ammunition and free of apparent issues. The bomb load is finalized with triplets of retarded high-explosive bombs loaded onto the wing pylons by the ordnance crew, utilizing a specialized jack-up bomb trolley. Safety pins are inserted to secure the bombs before the trolley is removed. And safety wires are affixed to each bomb to prevent arming until after release. As it falls, the wire breaks, thus freeing the nose-mounted propeller to turn the requisite number of times and so arm the weapon. The two crew members undertake the standard walk-around check before boarding the aircraft. With assistance from the ground crew, they strap in and then don their bone dome helmets and flame-resistant gloves. The next task involves conducting a cockpit check with the aid of a specialized checklist. All moving surfaces undergo a final visual inspection and testing as the ground crew remove flagged pins and safeties, which are then prominently displayed to the pilot. Loaded with 12 bombs and a centerline drop tank, the F-4B of Marine Fighter Attack Squadron 115 taxis out for takeoff, accompanied by other Phantoms slated for the mission joining up on the runway. Before receiving clearance for takeoff, the crew verifies that the outer wings are securely locked down, then proceeds to embark on another tactical sortie in support of Marine Corps ground forces. As the scope of US operations in Vietnam expanded steadily during the later 1960s, there was a corresponding increase in the expansion and enhancement of bases utilized by aircraft like the Phantom, which necessitated fully paved runways. Marines are depicted laying a temporary extension to a paved runway in the image. Ground operations necessitated support around the clock and in all weather conditions, highlighting the crucial role played by Marine Aviation Phantom squadrons in facilitating the success of Marine Corps ground forces in Vietnam. Phantom pilots took pride in their ability to deliver a wide array of ordnance with precision, particularly in close proximity to friendly forces' forward positions, a capability that proved pivotal in crisis situations. The ability to rapidly respond allowed constant pressure to be applied on the enemy, whose precise location was communicated via radio relay by ground forces or a forward air controller. Waves of aircraft ensured sustained air pressure on hostile ground forces and enabled the deployment of various types of ordnance tailored to the circumstances of each tactical scenario. The US Air Force emerged as a major operator of the Phantom in Vietnam, commencing with the F-4C land-based variant of the F-4B, followed by the modestly improved F-4D featuring enhanced ground attack capabilities. Despite susceptibility to communist guerrilla attacks, centralized fueling systems like the one at Cam Ranh Bay offered tactical advantages, prompting their utilization in Vietnam. The Phantom's high fuel consumption posed challenges for holding quick reaction units on the runway, but often circumstances demanded it to swiftly deploy maximum aerial firepower against communist forces. However, this practice exposed crews to heat fatigue under the scorching tropical sun while waiting fully manned and armed on standby. Despite these concerns, the paramount consideration remained the speed of reaction, ensuring Phantoms could be scrambled promptly when needed. After the standard preparation and takeoff, sometimes with reduced fuel to allow the maximum possible war load to be uplifted, the Air Force's Phantoms often linked up with a Boeing KC-135 tanker to top up their tanks and thus increase combat radius with a war load of up to 16,000 pounds of external stores. Here, the boomer aboard the tanker aircraft guides the boom into the Phantom's dorsal receptacle for fuel transfer. Renowned as the quintessential attack aircraft in Vietnam, the Phantom offered an impressive combination of payload capacity and range, coupled with robust airframe strength and advanced avionics, ensuring precise targeting with remarkable accuracy. This footage, captured during an attack, vividly demonstrates the Phantom's capability to engage heavily defended targets in North Vietnam as effectively as less fortified targets of opportunity in the war-ridden terrain of South Vietnam. Targets outside of South Vietnam included critical communication networks, power plants, and strategic stockpiles, all heavily guarded by anti-aircraft artillery and missiles. Even in adverse weather conditions, Phantoms demonstrated their ability to penetrate defences and deliver their payloads. The Vietnam War saw the deployment of the entire spectrum of tactical weapons by the USAF, encompassing various types of freefall and retarded high-explosive bombs. Retarded bombs were specifically designed to allow attacking aircraft to drop them accurately at low altitudes to maximize the force of the explosion. In coordinated operations, Phantoms would operate in tight formations at medium altitudes, with all aircraft releasing their bombs upon the leader's command to achieve maximum concentration of ordnance. Napalm emerged as a particularly vital weapon in the US tactical arsenal during the Vietnam War. While the initial F-4C proved effective, it underwent development into the F-4D with enhancements such as the APQ-109A radar replacing the APQ-100 and the ASG-22 sight. However, both models lacked an internal gun, leading to the frequent use of cannon pods in both air-to-air and air-to-surface roles. Pictured here is an SUU-16A pod loaded with 1,200 rounds of 20mm ammunition. The pod incorporates an external ram turbine to power the cannon, restricting the aircraft to speeds below 400 miles per hour during the firing pass. Thus, its use was confined mainly to the air-to-ground role, as demonstrated in these sequences of typical ground attack passes. The SUU-16A and the SUU-23A self-powered versions, designed for high-speed air-to-air engagements, served as solutions, albeit not ideal ones, to the Phantom's lack of an internal gun. Additionally, the Phantom operated with air-to-surface missiles, like the 12,000-yard range Bullpup. As previously mentioned, its primary air-to-air armament consisted of the medium-range Sparrow and short-range Sidewinder missiles. Although air combat was infrequent during the Vietnam War, encounters with MiG fighters did occur, often resulting in successful engagements, such as the one depicted here with a Sparrow missile, or through cannon fire, as captured in classic camera gun footage. The definitive USAF version, the F-4E, introduced an M61 Vulcan 20mm cannon in the lower nose, along with the smaller diameter APQ-120 radar, uprated engines, a slotted tailplane, and maneuvering slats on the outer wing panels. Similar to earlier Phantom variants, provision was made for podded electronic countermeasures like the jammer pod, seen here, carried in the port-forward Sparrow missile recess. The Phantom quickly garnered significant export orders and emerged as the Western world's most vital tactical fighter. The Phantom saw service with 11 overseas operators, including Australia, Greece, West Germany, Turkey, South Korea, Japan, Iran, Egypt, Israel, Spain, and the United Kingdom. Despite not being the third largest purchaser of Phantom aircraft in terms of numbers, the UK pursued a significantly modified variant derived from the US Navy's F-4J. Designated as the F-4K for the Royal Navy and the F-4M for the RAF, this variant featured two Rolls-Royce Spey afterburning turbofans. This necessitated substantial revisions to the fuselage, although the additional drag resulting from these modifications offset the advantages of the more powerful and fuel-efficient power plant. The naval variant, known as the Phantom FG Mark I, boasted the AWG-11 fire control radar and incorporated various British features. Its armament included the Sparrow missile and the 2-inch rocket, the latter housed in multiple pods mounted under the wings. The FG Mark I remained in service with the Fleet Air Arm until the Royal Navy was forced to phase out its fixed-wing carrier strength in the mid-1970s. Following the allocation of survivors from the Fleet Air Arm's 52 aircraft, the Royal Air Force operated the Phantom FRG Mark II, equipped with the AWG-12 fire control radar and a British navigation attack system. Peacetime ground attack training typically involved rockets, cannon pods, and practice bombs, as depicted in the accompanying sequence.
Roger, about 5 degrees coming on to the attack heading now. Contact the target, master arms going on, and the camera's going on. Going right a bit. Firing now, and pulling. Downwind now for Florida landing.
Roger, Red Leader, join.
Gears down. On speed.
The 150 British Phantoms primarily serve in air defence roles over the UK, with a secondary responsibility for fighter ground attack missions. Number 41 Squadron exemplifies one of the 7 British Phantom squadrons, with 2 squadrons flying ex-naval FG Mark I variants and a 3rd squadron operating ex-US Navy F-4Js. The latter was necessitated by the RAF's increased commitment in the South Atlantic following the Falklands War of 1982. Modern developments have highlighted alternative roles for the Phantom, such as reconnaissance and defence suppression. One of the most significant developments has been the creation of the F-4ES, high-altitude photo reconnaissance variant of the F-4E, exclusively utilised by Israel. This variant features a completely modified nose section to accommodate special HIA C1 oblique photo equipment, enabling the high-altitude aircraft to surveil deep into enemy territory while remaining in the relative safety of friendly airspace. Israel is also undertaking upgrades to its fighter models. Additionally, countries like Japan, South Korea and West Germany envision a future for their fighters, following extensive upgrades by their respective aircraft industries. Throughout its service history, the Phantom has demonstrated remarkable adaptability across a wide range of roles, utilizing various weapon types on its 5 hardpoints. Some of the most important are illustrated in the next few sequences. Unguided rockets have played a particularly significant role in area ground attacks. Among the most commonly utilized types are the 2.75-inch rockets, with the 5-inch variants being less frequently employed. These rockets are fired from launchers of various sizes and are effective against soft battlefield targets such as troop concentrations, unarmored vehicles and artillery positions. In the air-to-air role, the short-range infrared-guided Sidewinder has proven more successful than the medium-range Sparrow. The Sidewinder locks onto the heat emitted by the target, providing reliable targeting compared to the Sparrow, which homes in on radar reflections bouncing off the target. The Phantom can carry up to 4 Sparrow missiles under the fuselage and 2 or 4 Sidewinders on underwing hardpoints, offering maximum flexibility in air-to-air engagements. In the depicted sequence, a Convair F-102 Delta Dagger pilotless drone serves as the target. A late-model Sidewinder successfully hits the drone's tailpipe, demonstrating the effectiveness of the weapon. Following the successful hit, the drone experiences successive breakup as it tumbles out of control. Both saturation and precision bombing have been conducted against point and area targets, utilizing a wide range of US bomb types, including highly effective high-blast demolition types. Cannon pods have also proven highly successful in the air-to-ground role, with 20mm pods being more common, although 30mm pods can also be carried. Multiple pods have demonstrated devastating effectiveness in air-to-surface operations. As the most important type in US Navy and US Air Force service during the 1960s and early 1970s, the Phantom was utilized by aerobatic display teams of each service. The Navy's team, the Blue Angels, operated the F-4J until the rising fuel prices necessitated a change to the McDonnell Douglas A-4F Skyhawk in 1974. Similarly, the Air Force's team, the Thunderbirds, flew the F-4E until transitioning to a smaller and more economical type. In this instance, the Northrop T-38A Talon. The Phantom stands as the Western world's most widely built and extensively utilised combat aircraft since World War II, making its production milestones notable achievements in aviation history. The 1000th Phantom, an F-4B for the US Navy, was delivered on July 7, 1965. 2 years later, the 2000th Phantom, an F-4D for the Air Force, followed on February 21, 1967. Just 17 months later, on August 28, 1968, the 3000th Phantom, an F-4J, was produced for the US Navy. An F-4E for the Air Force became the 4000th Phantom on February 1, 1971. Finally, on May 24, 1978, the 5000th Phantom, an F-4E, was delivered to the Turkish Air Force. Although the Phantom is no longer in production, it remains an effective warplane. A classic fighter isn't just one that performs well under ideal conditions, it's one that accomplishes missions beyond its original design. The success of the Phantom was a result of the courage and skill of its crews, supported by an aircraft that was capable and versatile enough to adapt to various missions. The F-4 Phantom was neither pretty nor elegant, but it did its job when so many other aircraft in history could not. That's what counts.
This is the McDonnell Phantom II, a powerful and steadily growing force for the defense of the free world. This is a pilot's airplane, and the Phantom's flight crews have adapted quickly to the aircraft's power and ease of handling to demonstrate time and again that this is the most versatile air weapon in the world. They have demonstrated it not only in official military tests, but by a series of official world records, which stand as a reassurance to America and her friends, and a warning to her enemies. The Phantom has 2 engines for power and reliability, and 2 crewmen for efficient weapon delivery. As an interceptor, it carries both heat-seeking sidewinders and radar-guided Sparrow missiles to destroy attacking aircraft. For long-range attack and troop support, the Phantom can deliver a wide variety of conventional or nuclear weapons. As a Navy fighter, the Phantom operates from aircraft carriers. It can fly efficiently from World War II carriers with their limited deck space, as well as from the latest supercarriers, taking full advantage of their multiple launch facilities. Its stable landing approach brings it safely aboard.
This same slow flight capability also enables it to operate from relatively small land bases. Many other capabilities have been proved by strenuous test programs: range, speed, endurance, and reliability. These qualities were emphatically demonstrated as the Navy showed the Phantom's performance to the world by an all-out assault on existing world records. A look at these records will dramatically illustrate the fighting power of the distinguished Phantom II. An intruding bomber, for instance, may be flying at an extremely high altitude. To down the enemy before he can strike his target, an interceptor must be able to take off and climb swiftly to his altitude. Early in the development phase, Project Top Flight proved the zoom climbability of the Phantom. Carrying recording instruments sealed by officials of the National Aeronautics Association, Commander Larry Flint took off from Edwards Air Force Base in California in an attempt to better the existing altitude record. After a level flight speed buildup, peak altitude would be reached in a zoom. His momentum carried him upward into the stratosphere to an altitude of 98,557 feet. As the aircraft dived toward Earth, instruments in the aircraft, as well as those on the ground, indicated that the Phantom had set a new world altitude record. This was confirmed by the Fédération Aéronautique Internationale and its American affiliate, the National Aeronautic Association. An effective interceptor must also be able to hold a high altitude for a sustained period to reach out toward the enemy before he reaches his target. Another world record demonstrated that the Phantom can do this too. Top Flight was a zoom above the normal operating altitude. This time, Commander G.W. Ellis flew through a straight 25-kilometer course at 66,443 feet to establish a new world record for sustained altitude. He maintained an average speed well over Mach 2 through the course. This record, like all the Phantom's other records, was made official by the FAI. Split seconds assume immeasurable importance as an interceptor moves to launch its missiles against incoming attackers. Here, the Phantom's speed pays off. Speed that has been proved officially 3 times, both in straightaway flight and in turns. One of these races against time was Project Skyburner. Its purpose was to establish the all-out straight and level speed of the aircraft, and thus demonstrate its ability to attack and re-attack evasive targets. Radars and optical trackers followed as Lieutenant Colonel Robert B. Robinson flashed through a straight 15-kilometer course over the dry lake near Edwards Air Force Base. As required by FAI rules, he turned and repeated the run in the opposite direction, reaching a peak speed of over 1,650 miles per hour. His average speed of over 1,606 miles per hour, Mach 2.57, made the Phantom the fastest jet-powered aircraft in the world. But straightaway speed is not enough. To utilize its multiple missile load against enemy bombers, the fighter must be able to turn and maneuver at high speed and altitude. The Phantom proved this capability in 2 record-breaking flights around both long and short courses. The first course was a 500-kilometer triangle. Precise maneuvering was required to enter the starting gate at high speed and on course, and to negotiate the sharp turn at the far end. Colonel Thomas Miller flashed around this course at an average speed of over 1,216 miles an hour. This was 400 miles an hour faster than the previous record. Another record was slated to fall as Commander John F. Davis took off for an even more exacting flight over a 12-sided course, only 100 kilometers around. Maneuvering precision was critical. The pilot was guided only by a radar plot, and if one wingtip should slide inside the markers, he would be disqualified. On the other hand, if he should fly too wide, his flight path would be too long, and his calculated speed would therefore be lower. But careful planning and practice paid off. On the record flight, Commander Davis held the Phantom in a steady 3G turn at 45,000 feet, averaging over 1,390 miles an hour. Once again, the data showed that the Phantom had set a new record. McDonnell engineers designed the Phantom to be an attack bomber as well as a fighter, and its bombing capabilities, too, have been well illustrated by official world records. Let's look at Sageburner. One very effective bombing technique is to approach the target at high speed and low altitude, thus hiding the aircraft from enemy radar and observation, and gaining the advantage of surprise. To demonstrate the Phantom's suitability for this type of attack, the Navy undertook to fly a straight 3-kilometer course at top speed, less than 300 feet above the ground. Lieutenant Hunt Hardesty as pilot and Lieutenant Earl D. Esch as radar observer made repeated supersonic passes over this course at an average speed of 902 miles per hour, Mach 1.2, averaging only 125 feet over the terrain, and sometimes flying as low as 50 feet. The density of the air at this extremely low altitude, coupled with supersonic speed, made severe demands on the pilot's skill, as well as the structural strength and controllability of the aircraft. Announcing this world record, Admiral George W. Anderson, Chief of Naval Operations, said, "The 3-kilometer record is one more bit of proof that the Phantom II is one of the best fighter aircraft in the world." The world is the Phantom's sphere of influence. In fact, operating from carriers and existing friendly shore bases, the Phantom can bring its fighting ability to bear on 96% of the world's surface, and do it quickly and efficiently. Project Lana proved the Phantom's long-range speed. Lana commemorated the 50th anniversary of naval aviation by showing the Navy's ability to deploy rapidly to far-off trouble spots. A group of Phantoms, equipped for combat, crossed the country non-stop from coast to coast, faster than any aircraft had ever done before. The start was from Ontario, California, and the finish line was New York's Floyd Bennett Field. The fastest plane of the group would also win the famous Bendix Trophy. There were 3 in-flight refueling points over New Mexico, Missouri, and Ohio. When all was ready, the starting command came from NORAD headquarters. The Phantoms roared off the runway at Ontario at timed intervals. The Air Defense Command and the Federal Aviation Agency had organized an electronic network for flight surveillance and communications. At the first refueling rendezvous, the Phantoms dropped to the tanker's altitude and slowed to match the tanker's subsonic speed. Then, fuel replenished, they were off again at their own high altitude and supersonic pace. After the 3 lead Phantoms completed all refuelings, they began their letdown. All 3 broke the record. The best time was set by Lieutenants R.F. Gordon and B.R. Young in the 3rd Phantom. They had spanned the country in 170 minutes at an average speed of over 869 miles per hour. These official records, impressive as they are not only significant for themselves alone. They serve to show the people of the world the true power of one of America's newest and best defenders of freedom, the versatile Phantom II.
The F-4 Phantom II is a versatile tactical fighter. It can be used as a fighter bomber, interceptor, or as an air superiority fighter. To gain and maintain air superiority is in part the mission of the Tactical Air Command. F-4 pilots assigned the specific mission of seeking out and destroying enemy aircraft in the air and on the ground must understand and be proficient in aerial combat maneuvering. Air-to-air combat is a swift and deadly game. Victory or defeat may be decided in only a few seconds. Mission success, and usually your life, depend upon a thorough knowledge of your weapons and weapon system, as well as those of the enemy. Pilots assigned combat duty will be exposed constantly to situations where only the most skillful maneuvering, teamwork, and timely application of basic air combat tactics will enable them to emerge victorious. Flying the F-4 in air combat tactics training, as well as in combat itself, demands an ability to maneuver the aircraft at maximum performance. To do this, the pilot must have an understanding of adverse yaw and dihedral effect. Adverse yaw is defined as yaw that is opposite to the desired direction of turn. At subsonic speeds and high angles of attack, rudder must be used in the F-4 to offset this yaw. This yawing moment is caused in part by the aileron on the top wing, left wing in a right turn, being deflected down and causing more drag than the spoilers on the low wing, because these spoilers are operating in a lower pressure area. One example of dihedral effect, and perhaps the easiest to understand, is the characteristic of any swept-wing aircraft to obtain more lift from a wing that is straightened out into the relative wind. The opposite wing is, in effect, swept further back. For this reason, the F-4 can be rolled with rudder. When performing a hard turn, as angle of attack begins to increase, the pilot may be tempted to tighten the turn by using more aileron. This adds to the undesirable condition, and if these improper controls are held, a snap rollaway from the desired turn may result. This could be disastrous in combat. To prevent a snap roll or post-stall gyration, the pilot must, when subsonic at high angles of attack, use rudder to control roll rate and bank, hold the ailerons neutral, and control turn rate with backstick pressure. Caution: develop a feel for the rudders. Do not arbitrarily jam full rudder in the direction of turn, or dihedral effect will cause a roll in the direction of applied rudder. With proper training, the F-4 pilot will have no trouble in developing a feel for his aircraft and flying it to maximum performance. Remember, you are flying the airplane, not riding it. The basic fighting unit is the two-shift element. It is much more maneuverable than a flight of four. The leader must, however, spend a great deal of his time clearing the wingman rather than looking for potential targets. When the element is used as a part of a flight of four, the wingman flies a position 1,000 to 3,000 feet out from the lead, depending on altitude, and from line abreast to 20 degrees back. Flying this position, the wingman can cover the leader's 9 o'clock to 3 o'clock area through the rear hemisphere, his primary area of responsibility. During turns, the wingman maneuvers in the horizontal and vertical planes. By playing the outside as well as the inside of the turn, the wingman can easily maintain position, conserve energy, and provide visual coverage in the rear hemisphere. When on patrol, the wingman stays well forward in easy view of the leader. He maintains coverage in the rear hemisphere while the leader searches for the enemy. The distance between aircraft may be increased at higher altitudes due to increased enemy missile performance. This increased separation extends visual coverage in the rear hemisphere, moving the blind spot farther out. Upon initial contact with the enemy, the wingman must move to the maximum performance maneuvering envelope. The size and shape of this envelope varies, but generally it is a cone 60 degrees to 90 degrees from the leader and 1,000 to 1,500 feet back. These distances and angles may vary as long as the wingman is able to provide mutual support and visual coverage during violent maneuvers. The primary duty of the wingman while flying in the maximum performance maneuvering envelope is to provide coverage in the rear. To maintain position and to perform his duties, the wingman will need a degree of skill and proficiency which is gained only through practice. When flying in the maximum performance maneuvering envelope, the wingman provides the leader with a spare weapon system, should his own malfunction.
My gun's jammed. Take him, too.
Should this occur, the wingman moves forward, assumes the lead, and maintains whatever advantage the leader may have had. If at any time the wingman cannot perform his duties, he should notify his leader immediately. The offensive potential of the two-ship flight is greatly enhanced when it is used as part of the basic combat patrol formation. This is a four-ship flight comprised of two mutually supporting elements. In this formation, the leader plans the attack and engages the enemy. The number 3 man, or element leader, supports the flight leader and assists in the attack. The number 2 and 4 men support their respective leaders and cover the vulnerable 6 o'clock areas. Since the element leader functions as alternate flight leader as well as leader of his own element, he is selected for his demonstrated leadership, ability, and aggressiveness. The supporting element is flown 3,000 to 9,000 feet out from the leader, and 0 to 5,000 feet up. These distances will depend upon altitude, configuration, and mission requirements. This is because of decreased enemy missile performance in denser air and the difficulty in seeing camouflaged aircraft at low altitudes. Visual contact must be maintained. While on patrol, the element leader may maneuver his element from a position of line abreast to a maximum of 10 degrees back. During turns, the element maintains this position by energy-altitude trade-offs. Generally, this type of maneuvering will require one crossover for every 90 degrees of turn. The leader will usually turn 90 degrees or in 90-degree increments. If not, he'll inform the element leader so that he may plan his crossover so as to be in correct formation position when the leader rolls out. There are 2 points that deserve special emphasis. First, wherever possible, the supporting element is flown down sun. Second, great care must be taken when crossing over in the fluid 4 formation to prevent mid-air collision during the brief periods of reduced visual contact. Correct employment of visual search techniques by each member of the flight will provide good detection rates at ranges of 3 miles or more in the rear hemisphere. The flight leader searches the forward hemisphere from 15 degrees above the horizon downward. The lead also makes casual checks of his element and its rear area. The element leader, in addition to maintaining his position, searches the forward hemisphere from 10 degrees below the horizon upward. The right wingman searches the area from the flight leader's 9 o'clock position to the rear as far as he can see. The left wingman searches the area from the support leader's 3 o'clock position to his rear as far as he can see. The use of small check turns will improve the 6 o'clock coverage by displacing the blind spot from side to side. Laxity in performing scan responsibilities cannot be tolerated. This is equally true in regard to radar search. Radar coverage in a flight of 4 is improved when each flight member searches a definite area with a minimum overlap. The lead aircraft selects 1-bar scan, radar mode, 50-mile scope, and adjusts the antenna elevation so that approximately half-inch ground return appears at the top of the scope. This radar search pattern supplements the leader's visual search area. The rear seat pilot maintains constant radar surveillance of his area. The number 3 man or supporting element lead selects 3-bar scan, radar mode, 50-mile scope, and adjusts the antenna to obtain half-inch of ground return on the lowest sweep. He then selects a 1-bar scan, thus automatically raising the antenna to the desired elevation. This radar search pattern supplements the element lead's visual search area. The number 3 rear seat pilot, like the lead rear seat pilot, concentrates exclusively on radar scan. The number 2 man selects 1-bar scan, radar mode, 25-mile scope, and adjusts the antenna so that half-inch of ground return appears at the top of the scope and maintains that search position. While the number 2 aircraft commander is scanning his visual search area, the rear seat pilot divides his time evenly between the radar and a visual scan of the same area scanned by his aircraft commander. The number 4 man selects 1-bar scan, radar mode, 50-mile scope, and adjusts the elevation strobe to 8 degrees up. He then selects 3-bar scan for search. The rear seat pilot in the number 4 aircraft, like the number 2 rear seat pilot, divides his time evenly between visual scan and radar scan. The number 4 aircraft radar scan area combined with the number 2 radar scan area provides a thorough long-range detection capability in the forward hemisphere when combined with the visual and radar scan of the lead and supporting element. It can be said that the air battle consists of 3 phases: acquisition, maneuvering, and terminal. Acquisition. You must find the enemy to engage him. Maneuvering. You must outmaneuver the enemy to destroy him. Terminal. You must know your weapons and weapon system to hit him. The F-4 has an excellent long-range air intercept radar. If properly used, this radar can be a decisive factor in the air battle. With this long-range detection capability, it is probable that contact will occur in the forward quadrant prior to visual contact. The problem of visual identification of bogies must receive special attention. proper interpretation of radar returns can provide valuable information at sufficient range and time to allow the attackers to maneuver to gain tactical advantage prior to visual contact. When equipped with all aspect missiles and in a front hemisphere attack, separate the elements to achieve a first-pass ID and missile launch. A good rule of thumb to determine minimum contact range necessary to gain the separation for attack is approximately 3 times optimum missile range. For example, if optimum missile range is 5 miles, then minimum contact range is 15 miles. If contact is made at sufficient range, the ID element should make a descending acceleration using afterburner to 1.2 Mach. The launch element executes a barrel roll or S maneuver to obtain desired separation in minimum time. While gaining separation, the ID element wingman should make a thorough radar search of the area for other aircraft that could be a threat. The ID element lead maintains radar contact and maneuvers for a collision course. After allowing the ID element to gain the desired separation, the launch element also accelerates to 1.2 Mach and maintains a target lock-on while keeping visual contact with the ID element. As soon as visual ID can be made, the ID element lead relays to the launch element lead the identification of the target aircraft, and, if it is enemy, clears him to fire.
MiGs, 21s. No missiles on board. Clear to fire, clear to fire.
If the ID element is undetected passing below the enemy, or if the enemy fails to maneuver, the ID element should employ basic fighter maneuvers to re-attack or support the launch element. If, however, the ID element is detected and the enemy maneuvers against it, they may employ counter-maneuvers against the enemy or continue a straight-ahead run-out, while the friendly launch element sandwiches the enemy. When the ID is made and clearance to fire received, the launch element executes either a front or a rear hemisphere attack, depending on the enemy's actions. Both elements then engage the enemy, supporting each other until the enemy is destroyed. When attacking from a beam, the separation required is less, and it is easier to attain. On the initial visual identification pass, the ID element may fire if identification can be made soon enough. If not, he turns 180 degrees from the target's heading and maneuvers for a follow-up attack. The turn will put him out of the target area and allow the launch element a shot as they follow and maneuver for a missile or a gun attack. The two elements then fight as a team until the enemy is destroyed. In a stern attack, you must consider the range to target, fuel required to close, and your heading. A stern chase is useless if bingo will occur before identification or firing range. A stern approach, however, is the best position for surprise in a missile or gun attack. The elements in a stern attack maneuver so as to keep pressure on the enemy at all times and support each other until the enemy is destroyed. When operating as a lone element and attacking a flight of 4, make either a beam attack or a stern attack, since identification and re-attack are the most difficult from head-on. Be very careful to maintain element integrity when attacking as a lone element, since look back from the F-4 is poor. After radar acquisition and initial attack, competence in basic fighter maneuvers is essential in destroying the enemy with either a missile or gun. The high-speed yo-yo is a good maneuver to maintain the advantage when on the attack. Its purpose is to maintain nose-tail separation. As you recognize an overshoot coming up, keep your G's on while reducing some of your bank. Slide high and inside the defender's turn. This will reduce your forward velocity while maintaining nose-tail separation. Watch your opponent and slide back down on the attack. Don't get the nose too low, or you may be forced out the bottom. The low-speed yo-yo is another good attack maneuver in the F-4. Lower the nose and establish your cutoff while nose low. Light the afterburner and accelerate to Mach 1.1 or more. Terminate afterburner and begin pull-up. When the nose is above the horizon, relight afterburner and slide up toward the defender's 6 o'clock. As you slide into your opponent's lethal cone, be prepared to perform a follow-up high-speed yo-yo. The barrel roll attack is an excellent offensive maneuver for a missile or gun attack. When the defender is turning into you while you are still at long range, 8,000 feet or more, and generating angle off, 40 degrees or more, begin the maneuver from low and inside the defender's turn. Play the rate of roll for the desired effect, depending on the range and rate of the defender's turn. If the defender is turning right, you roll to the left, and vice versa. Backstick and rudder is used throughout the entire maneuver to hold the nose in the desired position. Upon completion of the roll, you will find your angle off diminished and the range reduced. If G-load permits, fire a missile when in range. Press the attack and, if need be, execute another barrel roll attack or perform a high-speed yo-yo. While the fighter pilot and his aircraft comprise an offensive weapon, the possibility is strong that the first contact with the enemy will be in the rear hemisphere. This is due in part to the enemy's GCI capability. Thus, it is imperative that you have a thorough knowledge of both offensive and defensive maneuvers. The basic defensive maneuver is the defensive turn. This is a hard turn performed to prevent an opponent from achieving a launch or firing position. With this maneuver, the defender can diminish the lethal envelope and improve his position by rotating his cone of vulnerability away from the attacker. If the attack is discovered closer in, a break may be necessary. This is a maximum performance turn into the attack to destroy the enemy's tracking solution and force him to overshoot. The effect is gained in the first 45 to 60 degrees of turn. If the attacker does not yo-yo and overshoots, reverse, and if you're lined up, take a quick shot at him. If you are not lined up, get him out of phase and dive for separation. If an attacker has been forced to overshoot, another maneuver is the scissors. As the MiG overshoots, make a nose-high reversal and continue with a series of turn reversals. This will rotate your lethal cone away from the attacker and force him again to cross your flight path and eventually to your 12 o'clock position. The scissors is an effort to gain an offensive position. The advantage, however, lies with the aircraft having the shorter turn radius and the lower airspeed. For this reason, the Scissors is not considered a good maneuver against the lighter, more maneuverable MiG series aircraft. After the first couple of reversals, if you cannot get a shot, watch the MiG. Get him out of phase with you, and when he cannot see you, roll rapidly. Engage the afterburner, pull the nose down to vertical, and accelerate out. Bear in mind, you need altitude for this. Should the MiG follow close in, you may set the hook. As he commits himself nose low, reduce power, extend speed brakes, and pull up at maximum performance. This should throw the MiG out the bottom. Roll off and drop in on him. If the MiG does not follow close in, do not set the hook. Accelerate out to at least Mach 1.1, descend to low altitude, and gain separation. A moderate 2G roll while descending should be enough to spoil the MiG's tracking solution on the way down. When on the deck, make random reversals to keep him from getting a tracking solution, while you use the F-4's advantage of speed at low altitude to outdistance the enemy. When out of gun range, stay low if you're still within missile range. When you are definitely clear of the MiG, then pull up and re-engage head-on. When a flight of 4 F-4s is attacked by 2 MiGs, the element under attack should separate either by a straight-ahead diving acceleration or by a turn away from the free element. The free element then quickly sandwiches the attackers. Again, be doubly watchful for additional MiGs in the area. If both friendly elements are under attack, it may be necessary to fight as lone elements until one element destroys his opponent and is thus free to assist the other element. When defending as a lone element, the defensive split is a valuable maneuver to use instead of the last-ditch maneuver. With the MiGs approaching gun range, for example 4,000 feet out, and remember, that is 4,000 feet out from the wingman, and you are unable to force him out of your lethal cone, call for a split. The low man continues his hard turn into the attack, while the high man slides high, gaining separation on the low man. The attackers are then forced to make a choice. Take the low man, take the high man, split, fake at the low man, and then take the high man, or perform the fluid separation. An analysis of past engagements reveals that the MiGs are unlikely to fake or perform a fluid separation. The defenders must be on the alert. If the attackers split, each defender then defends himself and fights alone until he's destroyed his opponent before he can assist the other friendly aircraft. If the attackers take the low man, he continues the hard turn and goes into a diving spiral to gain separation, while the high man zooms up, then drops down to sandwich the attackers once they're line abreast. Should the attackers take the high man, he performs a moderate G roll-under, ending in a turn away from the low man. The low man then pulls up and sandwiches the attacker as quickly as possible. It becomes readily apparent that teamwork and radio discipline are mandatory for the defensive split. Proficiency in Fluid 4 and air combat tactics comes exclusively from training and practice. This proficiency is the only key to success. Air combat is a deadly game played for the highest stakes in the world. Your life and the life of your buddy. With so much to lose, there is no room for error. The knowledge gained in an aggressive air combat tactics program, combined with the skills developed in air-to-air gunnery training, will provide the tactical fighter pilot the tools necessary to engage and destroy the enemy in the fight for the sky. Good luck and good hunting.
Aviation, the art of aeronautics, began with the dreamers, inventors, and daredevils who dared to defy gravity. The journey of aviation was nurtured by pioneers like the Wright brothers, whose first flight marked a historic milestone. The role of aircrafts in world wars was groundbreaking, dramatically changing warfare strategies. This initiated a technological evolution in aviation, transforming the simplistic wings of a biplane into the thunderous roar of jet engines. Let's journey through the ages of aviation. Behind every great aircraft, there were great minds. These visionaries, like Sir Frank Whittle, the innovator of the turbojet engine, redefined air travel. Then there's Skunkworks Kelly Johnson, the genius behind the SR-71 Blackbird. His designs combined speed, stealth, and power, crafting machines that dominated the heavens. The contributions of these pioneers have left an indelible mark on the canvas of aviation, shaping the course of history and inspiring generations of engineers and aviators. Each epoch in aviation history gave birth to extraordinary aircrafts, each with their own unique features and roles. The Lockheed SR-71 Blackbird was a marvel of speed and stealth. The F-105 Thunderchief, a supersonic fighter bomber, was vital in the Vietnam War. The P-51 Mustang, a long-range fighter, was critical in World War II. The P-47 Thunderbolt, a heavyweight fighter, was used extensively in the same war. The A-10 Thunderbolt II, the Warthog, is a close air support icon. The Messerschmitt Me-262 marked a leap forward in aviation technology. Each of these game changers were instrumental in their eras, and their legacies still resonate today. Beyond the game changers, there are those that have transcended their practical roles to become icons. The Concorde was not just an aircraft, it was a supersonic symbol of luxury and speed. The B-52 Stratofortress, a strategic bomber, is an icon of power and resilience. These magnificent machines and others like them have become much more than just aircrafts. They are enduring icons that encapsulate the audacious spirit, the relentless innovation, and the boundless ambition that define the world of aviation. For more amazing aerial footage, and to join us in this incredible journey, check out the Dronescapes YouTube channel.
If you enjoyed this video, please remember to like and subscribe. And as always, thank you for watching.